Think about the night sky for a second. We look up, and even though we see countless stars grouped into galaxies, the overall view is deeply disorganized and clumpy. The universe seems messy. You have vast, bright clusters of galaxies separated by immense dark voids. But if we zoom out, far, far beyond the reach of any single galaxy cluster, we find a profound secret. The universe is incredibly smooth. Ask yourself this: what does smooth actually mean when we are talking about the entire cosmos? In cosmology, smoothness means the universe is uniform and isotropic. Uniform means that if you were to take a massive cube of space from one side of the universe and compare it to an equally massive cube of space from the exact opposite side, they would contain roughly the same amount of matter and energy. Isotropic means that no matter which direction you look, the universe looks the same. There is no preferred axis or special location. The proof of this cosmic smoothness comes from examining the faint, ubiquitous glow that fills all of space, the cosmic microwave background, or CMB. This is the oldest light we can ever hope to see, the true echo of the Big Bang. It is light that was finally released when the universe was only about 380,000 years old, a point before which the universe was too hot and dense for light to travel freely. The existence of this radiation was actually predicted decades ago by scientists extending the early Big Bang theory. George Gamow, a professor at the University of Colorado, along with his student Ralph Alpha and later Robert Herman, predicted that the universe should be filled with this thermal microwave radiation left over from the Big Bang. This prediction was spectacularly confirmed by its accidental discovery in 1963. When cosmologists measure the temperature of this ancient CMB, they find it is almost perfectly uniform, sitting at a temperature of about 2.7 degrees above absolute zero. The variations in this temperature are tiny, barely ripples, amounting to differences of only about 1 part in 100,000. These tiny fluctuations are what we call the seeds of structure, but the overwhelming uniformity is what defines its smoothness. The mystery lies in this uniformity. We live in a universe defined by clumps, stars, galaxies, black holes, and nebula. If the universe started out perfectly smooth, gravity would have nowhere to begin gathering mass. Gravity needs slight overdensities, tiny areas with a little extra mass to start pulling things inward. The fact that these massive structures exist proves the early universe was not perfectly smooth, it was only slightly rough. But the problem is that it was too smooth. Our intuition tells us that given the chaotic energy and extreme density of the Big Bang, matter should have settled into an uneven, clumpy mess, not this pristine, synchronized uniformity. The universe should look like an unfinished batch of batter, not a perfectly mixed foundation. The uniform conditions of the early universe as reflected in the cosmic microwave background matter because they establish the initial conditions for everything that came later, from the formation of basic elements to the scale of supermassive black holes. Think about the density of matter. We know that everything we see, stars, planets, and gas, is made up of normal baryonic matter, but the majority of gravitational influence in the cosmos comes from unseen dark matter. The existence of structures like the Milky Way, which contains hundreds of billions of stars, proves that matter successfully clumped together. This clumping could only happen if there were those slight initial density variations. If the universe had been born with major unevenness, the gravitational forces would have been so overwhelming that matter would have collapsed violently and instantly. Stars would have formed and burned out too fast, and the universe would have quickly become a cold, dark place after a chaotic initial flash. But instead, the CMB shows us a picture of near perfection, an incredibly high state of order or low entropy. The smoothness of the CMB is so precise that it provides a quantitative test of our cosmological models. The CMB light, which is uniform across the entire sky, started its journey when the universe was just 380,000 years old. At that time, the universe was hot, dense, and uniform. The subtle temperature fluctuations that exist, those small deviations from perfection, are exactly the right size to account for the gravitational seeds needed to grow the structures we see today, like massive galaxy clusters. Now, consider the profound improbability of this initial state. The universe began as an incredibly hot, compressed point. If we calculate the statistical likelihood of all the energy and matter in the universe starting in this highly ordered, low-entropy configuration, the numbers are astronomical. Roger Penrose, a famous theorist, calculated the odds of this specific smooth configuration arising by chance to be 1 part in 10 taken to the 10th power taken to the 123rd power. That number is so large it has more zeros than there are atoms in the observable universe. This means the Big Bang was the ultimate low-entropy starting point. The significance of this incredibly ordered beginning is that it provides the potential energy for cosmic history. The arrow of time, which dictates that disorder must always increase, only exists because the universe started in such an improbable state of order. This tension between the initial smoothness and the observed structure is what creates the central conflict in cosmology, the horizon problem. We need to understand how the universe achieved this initial smooth equilibrium when it expanded so fast that distant parts could never have interacted in time. The horizon problem is where the universe's smoothness clashes violently with the most fundamental rule of space-time, the fixed speed limit of light. Think about the most basic physics. Heat transfer, the process that makes things uniform, requires contact. If you have two objects at different temperatures, they must exchange energy until they reach equilibrium. For this to happen in the universe, light or energy must travel between two regions. But because light travels at a fixed, finite speed, there is a maximum distance that energy can travel since the Big Bang. Ask yourself this: given the age of the universe, about 13.8 billion years, how far could light have traveled from the Big Bang? That distance defines the cosmic horizon. We cannot receive information from anything outside that distance because the light has not had enough time to reach us. This is why looking out into space is literally looking backward in time. The farther the object, the older the view. The standard Big Bang model before modifications suggests that the universe was already quite large when the CMB light was released. If you look at the CMB coming from two regions of the sky that are separated by a large angle, more than about 2 degrees, those regions are so far apart that light from one spot has not had time to travel across and reach the other spot since the Big Bang. They are causally disconnected. They are outside each other's horizons. Now apply the principle of heat transfer. If two regions are separated and have never communicated, they should have wildly different properties. Imagine those two separate spots in the sky. One might have been born much hotter and denser, and the other much cooler and less dense. They would have had no way to mix or synchronize their energy. They should look completely different, reflecting chaotic, non-uniform initial conditions. But what do we observe? The CMB light coming from both distant regions is almost identical in temperature. They are synchronized to the same temperature, implying that they must have achieved thermal equilibrium at some point in the past. It is as if two people on opposite sides of the Earth set their clocks and temperature gauges to exactly the same reading without ever having spoken or shared information. This makes absolutely no sense under the standard model of cosmology that relies on the fixed speed of light and the universe's finite age. The uniform smoothness of the CMB across such vast separated regions is the horizon problem. This problem tells us that a fundamental assumption about the early universe must be wrong. The core mystery of the horizon problem is why distant regions look identical, despite being causally disconnected. The fact that energy uniformity exists across the entire observable cosmos is confirmed by analyzing the faint microwave light left over from the Big Bang. Think about this on the largest possible scale. The galaxies we see are grouped into colossal structures, sometimes thousands of galaxies strong, held together by gravity. Our own Milky Way is part of the local group, which contains other galaxies like the Andromeda Galaxy. When we look at the most distant parts of the universe, we are seeing the light that has traveled for billions of years. The universe is constantly expanding, a fact proven by the redshift of distant galaxies. As light travels through space, the fabric of space itself stretches, lengthening the light's wavelength. This stretching or cosmological redshift makes distant light appear redder and causes it to lose energy. This is how we use the universe as a measuring stick. The longer the light's journey, the greater the redshift, and the farther back in time we are looking. If the universe's expansion is constant, then regions on opposite sides of the sky should never have been in thermal contact because they receded from each other faster than light could bridge the distance. The simplest possible expectation, therefore, is a universe that is highly non-uniform and clumpy on the largest scales, reflecting areas that never synchronize their energy. Yet the CMB reveals a massive structure that is incredibly uniform. This uniformity is the missing light, or rather the synchronized energy that the standard model cannot account for. The only way two separated systems can look exactly the same is if they were once close enough to reach equilibrium, and then something suddenly and violently separated them. This required a radical rethink of the physics of the very early universe, specifically addressing the brief moment of existence before the CMB was released. The horizon problem is so severe that it demonstrates a major failure in our models of the Big Bang prior to the solution of inflation. The simple truth is that the universe's smoothness contradicts the fixed speed of light when considering the age and size of the cosmos. The universe itself had to perform a synchronizing maneuver when it was too small for the fixed speed of light to matter. The astonishing uniformity of the cosmos demanded a physical explanation that transcended the standard laws of expansion. The solution that most cosmologists accept, known as cosmic inflation, was conceived precisely to explain this deep mystery, the horizon problem. Think about the first tiny fraction of a second after the Big Bang. Inflation proposes that the universe, in an incredibly short period from about 10 to the negative 36 power seconds to 10 to the negative 24th power seconds, expanded exponentially. This means the rate of space's expansion was much faster than the speed of light. This doesn't violate Einstein's limit that nothing can move through space faster than light, but rather describes the stretching of the fabric of space itself. Inflation solves the smoothness problem by suggesting that the entire observable universe today originated from a single, microscopically small region of space. This initial patch was so tiny that light had no trouble whatsoever crossing it, ensuring that energy and temperature were uniform across the whole region, achieving thermal equilibrium. Once this tiny region was perfectly synchronized, the massive burst of inflation stretched it outwards at a terrifying speed, blowing it up by a factor of perhaps 10 to the 26th power. The result is that those regions on opposite sides of the sky, which seem to be too far apart to have ever communicated using light at speed, over 13.8 billion years, are simply separate parts of that tiny, original, synchronized patch that was inflated. The universe looks identical in every direction because, at its core, it is composed of material that was mixed and smoothed out before the rapid expansion began. Inflation also provides a powerful explanation for those tiny density fluctuations that allowed structure to form. Before inflation, the laws of quantum mechanics meant that the initial tiny patch contained unavoidable, random quantum fluctuations. These fluctuations, which are normally confined to the subatomic world, were suddenly stretched to macroscopic scales during the hyper-rapid expansion. These amplified quantum ripples became the gravitational seeds, the overdensities that eventually grew into dark matter halos, stars, and galaxies. Without inflation, we cannot logically reconcile the fact that the universe is both smooth enough to be uniform across vast distances and clumpy enough to contain the intricate structures of galaxies. Inflation is the necessary cosmic event that provides the synchronized, slightly rippled starting point needed for a universe like ours to exist. The idea that quantum mechanics, the physics of the very small, dictated the structure of the entire cosmos is mind-boggling, and it all stems from the need to explain the universe's surprising smoothness. The continuous expansion of space, combined with the initial smoothness provided by inflation, defines the long-term evolution of the universe and how structure grew. Think about the initial tiny fluctuations that inflation stretched out. These minute variations in density allowed gravity to begin its slow, patient work. Dark matter, which is the most common form of mass in the cosmos, acted as the gravitational scaffolding, pulling in baryonic matter, normal gas and dust, to form massive halos. This process converted the initial uniform energy distribution into the intricate web of galaxies we observe today. As we look out at extremely distant quasars, active galactic nuclei powered by supermassive black holes, SMBHs, we are seeing light that has traveled for billions of years, providing a direct view of the early universe. These quasars, which are powered by gas falling into the black hole's immense gravity, were about 100 times more common 10 billion years ago than they are today. This demonstrates that the activity and growth of structure were intensely concentrated in the past, confirming the non-eternal evolutionary nature of the cosmos. The expansion of space while resolving the smoothness paradox through inflation also plays a critical role in how we perceive and measure cosmic evolution. Because light travels at a fixed speed, looking at distant objects is inherently looking back in time. But as that light travels, the stretching of space dilutes the light and stretches its wavelength, causing cosmological redshift. This continuous stretching of light from distant objects is a direct measure of how much space has expanded during the light's travel time. For the most ancient galaxies, this redshift is so extreme that their visible light is stretched into the infrared spectrum, requiring specialized telescopes like the James Webb Space Telescope to observe them. The smoothness of the universe at the larger scales implies a uniform rate of expansion throughout cosmic history. If the expansion rate varied dramatically across different regions, the measured redshift and the cosmic background radiation would be uneven. The consistency of the CMB proves that space expands uniformly, carrying the synchronized imprint of the early universe outward. This uniformity is a fixed property that dictates everything from the energy released by quasars to the eventual fate of the universe. The incredible smoothness of the universe is not a cosmic accident. It is a vital prerequisite for a stable, complex, and observable reality. If the universe had deviated even slightly from this fine-tuned order, everything we know would break. Ask yourself this: what if the initial density variations were much larger, say 1 part in 100 instead of 1 part in 100,000? Gravity would have seized control violently. Matter would have collapsed into ultra-dense objects almost instantly. Stars, if they formed at all, would have been short-lived, unstable giants that rapidly exhausted their fuel. The entire cosmic history would be one quick, chaotic flash, leaving no time for stable solar systems or the complex chemistry required for life to emerge. The elements necessary for our existence, like carbon, oxygen, and nitrogen, which were forged in stars and supernova explosions, would never have been safely distributed throughout the galaxy. Conversely, what if the universe were perfectly, absolutely smooth? If there were zero density fluctuations, gravity would have nothing to grab onto. There would be no overdensities to serve as the seeds for dark matter clumping or gas condensation. The universe would remain a uniformly smooth, dark, low-density fog of hydrogen and helium gas, preventing the formation of any structures whatsoever: no stars, no galaxies, and no planets. The necessary smoothness of the early universe is directly tied to its low entropy starting point. This low entropy is not just a statistical oddity, but the energy potential that allows the arrow of time to move forward and enables the long, slow, ordered buildup of complexity over billions of years. If the universe had been born with high entropy, time would effectively be static, and no meaningful change or evolution could occur. The smoothness is proof that the universe started in an impossible state of order, setting the stage for its dramatic, yet balanced evolution. The fact that the CMB is uniform is the deepest evidence we have of the Big Bang and inflation. If you want to understand space like a NASA-level analyst, quick without studying for years or paying thousands for a university degree, we have a free community that will help you. Link is below. The smoothness ensures that the universe is massive, stable, and predictable enough for us to study. When you look at the dark night sky, you are not just seeing emptiness, you are seeing the shadow of a cosmic past that was impossibly ordered, allowing for the slow, grand construction of every galaxy, star, and particle within our observable horizon. If you're curious about what prevents the matter in the universe, which is mostly empty space, from collapsing into a singular dense point, and the surprisingly weak force that dictates this structural stability, click here to Why Things Never Actually Touch video.